Yeah.
No.
You're not gonna do that?
No.
I chose chemical engineering at ASU specifically because I love the bioreactor side and the process control side of engineering. My research focuses on indirect oxygen sources in aeration tanks, specifically looking at hydrogen peroxide injection into these systems. What's so inefficient about current aeration tanks is that they have air bubbles being mixed up into the liquid, and the oxygen needs to transfer from a gas to a liquid, and so you have a bunch of transfer inefficiencies.
Close by here, the Mesa wastewater treatment plant, it receives a little bit over 10 million gallons a day of water. And so you can imagine that flow of water, the need to clean that water before it gets discharged, and how to do that effectively. And it turns out that we consume a lot of energy in these wastewater treatment plants. So we're trying to look at applications of how to treat our water in a more sustainable way, trying to reduce energy consumption. So bacteria need oxygen to consume the organics in the wastewater so that they can clean it. So you need to bubble air. Unfortunately, by bubbling air, you are also stripping chemicals out of the wastewater. And so you basically end up with another problem to solve, trying to clean that air.
Some researchers in the 1980s looked at hydrogen peroxide as a supplemental oxygen source or using it to achieve partial nitrification, but our work looks at it for being the only oxygen source in an aeration tank.
Well, we work a lot on bioelectrochemical systems, not only because we think that they're going to be useful, but because we think that these bacteria have a lot of potential. These are bacteria that make electricity. So we work a lot on understanding how these bacteria make electricity, how we can optimize it, and how we can use that process of waste to electricity. And that electricity can be used to make products themselves. And that's, part of the research that we do. I think one of the most interesting parts of our research is looking at the microbial nanowires that these bacteria produce. They make these conductive wires made out of proteins that have an iron center. It's a series of proteins that have an iron center, and they move electrons that way. And a single cell can have dozens of these nanowires coming out. And a biofilm has billions of these cells. So when you think about the amount of wiring that needs to happen in this biofilm, it's an incredibly complex electrical system.
My group does research in sustainable polymers. So think of it this way, we are producing 1 trillion pounds of polymers every year, plastics every year. And we are getting about 32,000 pounds that are ending up in landfills. We will eventually reach a limit where we don't have enough space to put our waste away. So the way I'm thinking about solving this plastic or polymeric material problem is by introducing this concept of self-healing. So when you think about biological systems, we are able to re-heal ourselves when we have damage, right? That's what sustains or maintains our functions. So we're trying to reintegrate those kind of functions in materials. But the problem is for self-healing, they need dynamic bonding interactions. And these dynamic bonding interactions tend to be weak bonds. The biggest trade-off or biggest challenge in creating high performance or mechanically robust self-healing is that you need the dynamic properties when we don't have that. And the way we're trying to introduce it is by introducing nanoparticles as cross-linkers. So we hypothesize that tuning that dynamic nanoscale interfacial interactions with the polymers, we can control what the bulk properties will be. So you still kind of use that non-dynamic polymer backbone so that you can have that mechanical stiffness and toughness that you want from the material. But because you have these sticky nanoparticles that can interact with this polymer matrix in a dynamic way, these nanoparticles can allow these polymers to be self-healing.
Why water? I think that water is a human right. And I think that everybody is deserving to have the basic needs. And by finding more efficient and less costly ways to clean water, we can implement these in places where it's not as feasible to have these large aeration tanks or high disinfection processes. The thing that I value a lot about ASU is that they work on collaborations and communities rather than individualistic work.
At a university like this, it has all the toys, like facilities and staff members who can help me run my research. You're not doing research alone, you collaborate, and from those you really learn something new and impactful.
We have a few core disciplines that we work on. We organize ourselves based on the research that we do, not on the discipline that we have.
Phoenix is one of the largest cities in the US, and so we have a very diverse population.
Sounds like you have a fun life.
Yeah, I know, it's yeah, I do really like Phoenix, it's really nice.